Okay, continuing our adventures in meteorology this week, we're going to talk about atmospheric circulations, particularly their scales of motion and general things about the atmosphere that way, just building up to more and more of the details that you're really interested in. So we have several different scales of motion. The macro scale, think of things that last for weeks. You could argue that the jet stream might be one because you can look at it all the way around the globe. Some monsoons that develop could be considered that because they cover large areas. Uh, so just things like that. While more things that are more transient become mesoscales. They go all the way down to about 1 nautical mile, like a thunderstorm or whatever. Then you have the microscale, which might be dust devils or even tornadoes. Uh, Downbursts would definitely fall in this category as well. Many downbursts are very tiny. So just some things beginning to look at the scales of motion. Everything is driven on Earth pretty much by the sun. We've already talked a lot about how the radiation works and how the sun affects and moves up and down across the equator throughout the seasons. Then you add the Coriolis force and you begin to change the way the air flows. If you just had the sun striking the equator, you would have air rise there because it becomes less dense, it's heated, and it would sink at the poles, both the North and the South Pole, because that's where it's cold and the sun doesn't come in much. So you would just have one huge circulation from all the way moving south from the poles and all the way up, back up above that, aloft, back to the north to the poles from the equator. However, we have a rotating Earth. So that causes three different, what we call cells to form. Three different major circulation systems. The Hadley cell, which is basically in the northern hemisphere, is northeast winds down between 0 and 30 degrees north. If you go in the southern hemisphere, it's southeast winds at about the same location. The Ferrel cell, which is between 30 and 60 degrees north, and this generally has southwest, even west winds in it. You live in the Ferrel cell, and that's kind of the area where most fronts, more air mass contrasts develop, where storms develop. And then you have the polar cell, like 60 to 90 degrees right at the North Pole. And if you look up at that very top of the Earth, or at the very bottom of the Earth, you don't have a lot of storms getting real close to the poles themselves. They're both fairly arid climates. And most of the precipitation falls south of there along the boundary, so that most of those, they tend to be in the cold air, most always in the Arctic or Antarctic areas. So just something to think about with that. Obviously, when you think about these circulations with Hadley cell there, you have convergence right by the equator, and that cell is going to move north and south depending on where the sun is. And with that, the ITCZ is going to move up north and then down to the south as well. That's just the intertropical convergence zone. That's where the two cells meet. And if you think about that, that means the southern hemisphere air is moving north into the northern hemisphere. And at some point, the northern hemispheric air is moving south into the southern hemisphere. So the two hemispheres actually trade winds and air masses throughout the year. And with that, there's plenty of rain typically along the ITCZs, especially across the waters. One thing to think about, where would the warmest air be during the seasons? Say you were to move coming to the summertime, summer solstice in the northern hemisphere. If you look at a map, part of the equator runs across land, part of it across water, the Atlantic Ocean. Well, if you think about it, the land is going to heat up a lot more and a lot faster than the ocean. So you almost wind up with the ITCZ a little bit further south over the water and a little further north over the land. So that you can actually see a shift between land and air than oceans. Now, if you go near 30 degrees north, you got lots of sinking motion there. In the summertime, we think about the Bermuda High along the east coast of the United States, and even out over the waters of the Atlantic a lot of the year. The southern Atlantic has a big high pressure sitting over it. That's typically right along 30 degrees north. You're not going to get much motion there. You have very little winds. They used to call it the doldrums when they were sailing ships across there. Now, when you get further north at about 60 degrees north, well, then you're going to have the northeast winds and the southwest winds converging there from the ferrule cell and the polar cells. Lots of temperature contrast across that area, and that's going to fluctuate. It's going to move south in the wintertime and north in the summertime. So that's why you have the seasons. That's why you have a lot more activity, more storms further south in the wintertime and further north in the summertime. So with that in mind, with all this sun, there are some areas that get really long-term monsoons. One of them actually is in the United States, in the southwestern U.S. If you think about it, the mountains in Mexico heat up, particularly in the summertime, and you wind up getting a lot of flow coming off the Gulf of Mexico towards those hot mountains that are in Mexico where all the air is rising. And then that flows up into areas such as Arizona. And you also have the other part of the Pacific Ocean rising into that area as well, pulling in some of the moisture from there. That's why if you look at starting in June, mid to late June, over Arizona and into New Mexico and maybe southern parts of California, even southern parts of Nevada, you're going to get a lot more thunderstorms there and different rain patterns. So just something to keep in mind that we actually have a monsoon in the United States. Southeast Asia, India, parts of the Middle East also have them. And we could talk in more detail about them as well. Jet streams, they're a big feature. We're going to talk a lot about them in the weeks ahead. We've already looked at them some, but you can see here there's a polar jet way up north, up here, close to the poles. More of a what they call the subtropical jet down to the south here. If you look off of California, you can almost see two jets splitting. You have one jet coming in towards California here and then trailing north up towards Alaska and across right along the pole up well up north, and that's what you can see happening here. And then you have another jet dropping south well off the southwestern U.S. and then across the southern part of the U.S. and then up. And they're actually come back together a little bit further east of the United States at this time. So it's something neat to watch how jet streams change and evolve. There's a huge jet stream across the Pacific Ocean here, and a lot of times you get that. And when it buckles, and that's when it kind of gets interesting because you can get storms and stuff moving along it. So one of the things in this chapter, it actually talks about climate of these jet streams and how they change from season to season. When you begin to look at weather for a long time, you'll notice things in the weather that seem to occur over and over again and that become kind of a normal. And they're kind of the climate of your area. If you live in Florida, for example, sea breezes develop in the afternoons almost all summer long in the central part of Florida. And if you would average over 30, 50, 100 years, that same area would almost always be the area that would receive it. You would see a spot that might have a little higher precipitation average over it. That's the climate that's developed down in Florida from that sea breeze that just constantly is there. The monsoons show a climate that they last over a long period of time. And many times you can look at storms as they develop and you say, okay, is this making any sense with what you would expect it to be in the climate at this time of year? Sometimes the computer models generate storms that don't seem to make any sense that way. When that happens, you're looking at it and saying, well, is there something happening in the atmosphere that's truly out of the ordinary? One of the things that has been developed is to actually determine how much below or above normal maybe the speed of a jet is, or the location of the jet is, or maybe where a low pressure is forming. Even southeast winds or winds at about 5,000 feet, which transports a lot of moisture in. By knowing that, you can determine the climate and maybe even figure out if this is an abnormal situation, or maybe the model's just wrong and you can actually develop a better forecast by going away from the model. So that's that one. So we'll take a look at air masses now a little bit. Air masses are, well, they just kind of, you're going to see them develop over a long period of time. And we're going to talk about air masses, fronts, and cyclones more in detail now. one of the things with an air mass, think about an air mass. Air mass requires temperatures and in the air itself not to change a whole lot. They gotta be over the same area. They gotta develop similar characteristics. If they're up north, they're not receiving as much sunshine, maybe in the wintertime. Maybe not receiving any sunshine at all if they're north of the Arctic Circle. So temperatures are getting very cold. There's snow underneath them. So that air mass is becoming and developing there as like an Arctic air mass. Well, maybe instead it's developing out over the Atlantic, like in the summertime when we see the Bermuda High. It's just sitting there, rotating right over Bermuda. Typically, the high sits. That air is developing. You'll feel the heat coming up off the moisture coming up off the Gulf Stream into it. So it becomes more humid. It's maybe not as hot as air masses that come in further from the west or whatever that actually come across the deserts. Maybe they're very dry. Maybe they've developed over the desert southwest, don't have a lot of moisture, but have a lot of heat in the summertime. So these are just things to look at for where the air mass is developing. And you're going to see that air masses don't necessarily move real fast, that they develop and they can tend to ooze in or down from that into other places. We're always looking at global circulations. We've talked about a lot of this here. Over the northern Pacific, you might get the maritime polar air masses. Fronts are just where two air masses intersect. Really, that's the basics of a front. And that can be a cold front where it's cold air is advancing. You think about it, cold air is always denser than warm air. So if that's the case, then warm air is going to want to rise over that cold air. And that cold air, the slope's going to be steeper if the cold air is advancing because the density is going to be much greater. And actually, you're going to see a quicker pressure drops if you look just above a cold front with height. If you look to the west of a cold front, for example, that's moving east, you'll see the pressure fall very rapidly with height because of that density. On the other hand, with a warm fronts are, again, the air is not as dense. When it's moving north, it's because the cold air is being allowed to leave. I had a professor once that told me a warm front can never move any direction without the cold air first wanting to leave that area. So it's almost always the cold air that begins to move away, then the warm front begins to advance. So usually there's something that is influencing that cold air to leave that area. And then you can move the warm front into that area. And with the warm front, again, it's going to come in aloft first. You're going to get the warm air overriding the cold air. And we've talked about stability this week, and I know that's always causes issues. But if you lift cold air upwards, and it's going to continue to cool, and it's going to hit that warm air aloft, even though the warm air might be a little chillier, having risen with time, it's most likely going to be stable. So it's going to wind up not being able to be lifted very fast. So what happens is you get a steadier rainfall or a lighter precipitation maybe. Now, right along the warm front itself, on the other hand, just to the south of that warm front is some very warm, humid air typically. And if that's getting lifted up into the system, well, then that's going to continue to rise up, and that might be unstable. Stationary front just means the front's not moving. It's very simple. So we'll look at some boundaries here on this weather map, and you can see we have a cold front over the eastern part of the United States, basically running from a low up over Canada all the way down to the Gulf of Mexico. Front's moving steadily east. You look at one of the things I've always was told as a student in meteorology, and when I talk to anybody, a cold front means air must be colder from where moving into warmer air. So there must be a temperature change, and sometimes in summertime that's hard to tell, but there almost always is a little bit of a temperature change with a cold front as it's moving in. The air is getting colder. The same would hold with a warm front. The air is getting warmer. In this case, you can really see it. Here it's 54 degrees. Out ahead of it is in the 60s. There, back in here, 37 degrees. We talked about the winds and how friction made a difference. Look how you would think the winds would be moving almost due north, and yet they're moving from the northwest in towards the low pressure that's over here and away from the high pressure. So, and here we look at a sounding. I wanted to show how much that cold front changes the air mass. A cold front came through Tallahassee, and at the top of that front, you can actually see an inversion. We've talked about temperatures getting warmer. Well, this is as far as that cold air has made it. So if I lift this parcel of air up right here, you'll see it's going to be much colder than the surrounding air that was already there. So it's stable. And it would continue that way upwards through that sounding. So that the low-level air down here, very dry, very stable air. And you can see the winds, how they shifted to the northwest here, and they were southwest just above that inversion. So what's happened is, if you were a pilot and you were flying through that area, you would see a sharp change in your wind speed, shifting from the northwest to the southwest, northwest being relatively light, maybe 10, 15 knots. All of a sudden, at a little bit over, about 3,000, 4,000 feet up, they become southwest at 45 knots. It's going to make a big difference on how your flight might react. Aircraft is going to change there. Atlanta sounding, this is the same cold front, just further north in it. And now, instead of the front being only about 3,000 feet thick, the front's up about 7 or 8,000 feet actually here. It's a little much thicker. Again, you still have that inversion above it though. But now the winds are more westerly all along, but it's not as steep of a jet there aloft or whatever. But again, you're still gradually getting more and more southwest winds with time. So it's just something to know that when you're flying across the cold front, as we talked about, is going to have a steepness to it, and you're going to be, if you're ascending or descending through near the edge of a front, you're going to be changing wind direction and changing temperatures as you go along. Extratropical storms, there's several models of them. Norwegian cyclone model was the very first. Basically, to have an extratropical storm, you need to have a strong temperature gradient. You need some kind of upper air support. You need some kind of divergence aloft. And hopefully, you're going to get convergence at the surface. And then you'll need that moisture. You want to add some instability into the mix. And really, the moisture is what drives that part. So, and the Norwegian cyclone model takes all of this into account. The conveyor model, on the other hand, it does the same thing, except it actually looks at like conveyor belts of moisture, conveyor belts of warm air, conveyor belts of cold air. So instead of just looking at the ingredients individually, it actually groups them together and picks, and actually think about it as literally a conveyor belt. So let's look at the cyclone development in the early stages here of little weak low over Texas. We're going to look at a jet stream. We have pretty good jet coming in on the California coast here. We have a little bit of a low kind of down over Texas. Left front quad usually has divergence with it and a jet. So you have a little bit of a jet in here and a curvature. And the way it is, a little bit of divergence down over Texas. Not a lot. If we were to look at 850, though, precip-wise, you're starting to see some moisture break out across Texas. And if you were to look at you got 850 temperatures here. You got a little bit of a temperature gradient here. You're gone from, plus 10, plus 15 Celsius across this area. So you have some temperature gradient in here as well. You have temperature gradient up here in the middle of the high as well, too. But there's, here's down here you have some moisture with it. You have the jet. So let's just look out in the future here a little bit. All right, that same front, same jet that was out to the west is beginning to start interacting with things in Texas now. You're getting a little bit better divergence over part of Texas right here in the left front. Another area you get divergence is the right rear quadrant of a jet stream. So you're getting divergence up in here as well. So with that in mind, so you're pushing this low very quickly to the east. Look how fast west to east flow you have across here. So here's your low. And with that, good convergence to the north of this jet up here, we call sinking motion. Guess where your high is? Right up north of that jet up in Pennsylvania and stuff. So it's right in this area where you have some convergence as well. So actually things are looking pretty straightforward here as far as where the low would be. Good temperature gradient again right in this area. Not a very strong low. That jet's gotten a little bit stronger now. You're starting to get better divergence in here. You're also getting some divergence from the northern jet as well now as the two are starting to come together. So these things kind of evolve with time, and you're starting to pick up. Now you actually have a low, not a very strong one, but off over the Carolina coast. Good rainfall coming back in. Temperature gradients actually beginning to tighten with time. You're pushing down colder temperatures with the high to the north, bringing in colder air, bringing up more moisture and warm air from the south out ahead of it. So you're developing that low as extratropical as it's getting along there. So just a couple points. We talked about it. Think about if you were flying across this low. When it initially was developing, you'd have a lot of low ceilings, low visibilities to the northwest of the low, while to the southeast of the low, you'd probably have a lot of Q thermals flying through, warm air mass there. If you're flying across, you probably have a boundary in there where winds were out of the northwest and then shift to the southeast with time. So, and with those jet streaks, you got to remember you're going to have lots of turbulence as well with time. We're going to talk a little bit, very briefly, about tropical cyclones. I'm really not going to show a whole lot here. You need a warm ocean for a tropical cyclone. Tropical cyclones are different than extratropical storms in that they don't want a temperature contrast. If they get temperature contrast, they're not going to develop as a tropical cyclone. They might develop as an extratropical cyclone, but they're not going to develop as a tropical cyclone. So you like a warm ocean, 80 degrees. That ocean is literally heating the air below it, providing lots of moisture, creating instability that's allowing the air to rise there. You get a weak disturbance, maybe an old frontal boundary that's come down and just kind of fading away, so it's lost its temperature contrast, but it might still have some upward vertical motion with it. That begins to develop some convection, maybe an easterly wave coming off of Africa. Then you begin to add the Coriolis force that begins to allow this little bit of a low to begin to turn, move a little bit, and pretty soon you begin to develop some kind of tropical system. A lot of times aloft. Remember we were talking about the divergence aloft and how you want the air to lift. Well, sometimes you get a very good high building across over top of these tropical cyclones, and that's where your divergence is. You can actually look sometimes all the way up through the whole atmosphere and see a very strong low at the surface. And going up through the atmosphere, you'll wind up with a very strong high right over top of it. That's not the case with an extratropical storm. There you have the low at the surface, and you'll go up to the northwest, and you'll see a strong low there as well. So they're very different in how they depict themselves. So if you want to know more, really look at these in the summertime when you're interested. The National Hurricane Center has a great webpage. It has tons of information about the storms. It has satellite views of the storms. It will give you lots of history about them. So it's a great source of just learning all about anything you ever wanted to know. If you wanted to learn, go back in time and look at things in the past. They have an archive there that goes back, I think, at least 30-some years or more. And you can really get a picture of just what's happened with the storms. So today we're going to take a little bit more of a plane ride around and see some things, but I want to talk about air masses. We're going to look at a global forecast model here. Notice the highs. All right, we have a high over Canada, and another high over Alaska, another high off the East Coast. So let's just loop this and just watch the location of the highs with time. Let's get it going here. All right, so we got one high sinking coming down out of Canada. But look back to the northwest over Alaska. Another high. It's been sitting here now for 12, 24, and it's really still sitting there. That's a new Arctic air mass forming. Literally right across, that high that had been here now is over New England, but there's still a high pressure back central Canada, back into the Alaska, right along that boundary. These are new air masses. It's literally a continuation of the same Arctic air mass, or in this case, maybe a Canadian air mass. So we wind up with one air mass right here, just continuing with time. So let's take a look at, maybe we can see another one develop. There's been a high sitting out over the Pacific Ocean in this area for most of this time as well. So maybe that high at the same time is developing more of a, not really a tropical, but a maritime. We'll say a maritime air mass. Not maritime tropical either, because the air is pretty cool out here. So probably maritime polar. It's just sitting out here and sitting out here, bringing its winds around it and stuff into the California coast. So it's a little bit more humid, maybe coming up into the coastline there. Maybe just a little tad below normal temperatures. So if you'll notice, look on a weather map and just see highs when you loop them that just stay in the same area. They're developing an air mass over top of them. And now you want to know, okay, if they're moving, when a piece breaks off, new high builds, maybe they're going to cause a front to be around them. In this case, high coming down here, another high off the coast, and we have a cold front right in this area moving across the eastern part of the U.S. and down. Out west, you have another front just north of that polar high, maritime polar air mass, more with the Canadian Arctic air mass to the north. And we were talking about the different cells and how they move along. Well, if you notice, this is real close to 60 degrees north with this high, maybe a little bit north of 60 even, some of it up in there. Some of it's below. So that's something that changes with the seasons. And that, where it would have been, the storms would have been at 60, maybe has dropped down to 50 now. And the high that would have been just north of 60, is now down around 60 or 50 degrees north. So those cells are going to fluctuate depending on the season. So let's take a look now at some satellite images. We're going to look at water vapor. Water vapor is a great depiction of where the moisture is coming from. It does show the drier air coming in. It shows an enhancement where there's storms, where there's rain. But to determine really how much moisture is in that plume of air, it's kind of nice to have some other tools to look at as well, like a sounding, for example, to see just how much moisture is coming along in here. Maybe you can see the jet coming in from California interacting in here. And by knowing where the air is coming from, maybe you can get an idea. If I have a lot of moisture like this coming across the northern part of Canada, I know it's got to go across the Rocky Mountains up here. That's going to take a lot of the water away with time. But what you see right here is a very nice, wrapped up, closed, upper level system. You're looking right now, most water vapor images really are up about 20,000 feet up, approximately 20 to 25,000. So you're seeing a good circulation at 20 to 25,000 feet. If you were to fly across this right now, your winds would change dramatically right across at that elevation across Texas and Oklahoma right now. So this is there's probably a nice jet stream right in here where the dry air, where the stratospheric air is mixing in. Also, think about it. You're putting dry air in on top of moist air over here. Well, we've talked about moist air cooling slower than a cold, drier air. Well, that's going to be the case here. So maybe this moist air didn't cool as fast as bringing in this dry air over top of it. So you become more unstable with time. So you begin to be able to lift the air parcel better. It's just something that you can look for. Sometimes you can see these things happening right along the edge of them where the moisture is. Now further back into the dry air, it's just too dry, not letting any instability go. But looking at this, just looping it here, let's just take a 12-hour loop of it. and you can actually see how that low is really closed off. And you can see where it's kind of almost separate from the circulations that were there. You have one up to the north moving around over here, but it's just kind of sitting there. So it's just something also to look at in the water vapor imagery. Let's take a look at the infrared imagery as well. And we'll look at 24 hours. We're going to loop it again. And we're going to see good thunderstorms. Remember that low really developing in here. But watch over the Gulf of Mexico with time as this thing moves. What you'll see here, look at these moisture starting to stream up out of the Gulf of Mexico, out ahead of that low and developing with time. So that really shows it right in here. And that's where the moisture is coming up from, the Gulf of Mexico, out ahead of that low. So again, if you were thinking about flying, going through there, you know when that low reached, this part of Texas here, it began to generate southerly winds, probably from about 3,000 to 4,000 feet, all the way up to about 8,000 to 10,000 feet out in here. And all that moisture, Gulf of Mexico is really wet. So it's beginning to lift that moisture north. Now you can look at it on the visible as well. Visible really shows lots of moisture coming up out of the Gulf of Mexico. Shows lots of bubbles along the East Coast too. Remember, we had a pretty strong cold front go through the East Coast and still all the way down into the northern part of Florida even. And this is still putting some cold air out over very warm or increasingly warm Gulf Stream. And when that cold air reaches the Gulf Stream, begins to gather moisture. It can't hold as much moisture as warmer air, so it forms lots of cumulus clouds, lots of thermals right in this area right now. So if you were to fly low level from Florida, say up to Hatteras, you would be hitting a lot of thermals across that area. So just something to look at on satellite, what you can see with time. All right, so now we're going to look at what's happening today, right now with the low. So let's take a look at the surface analysis. We were talking about cold fronts. Here's your cold front. That's a change of air mass. Notice the north winds. Again, notice how friction has changed. What would have normally been a northeast wind. It's northeast, but it's more north almost back in here because friction has turned it. Then you look down here at the south. Look at all this moisture we were talking about, looking at it on satellite. Dew points, measure of moisture, 70-degree dew points down here, 69. All that air, 60-degree dew point up into Little Rock, Arkansas, for example. All that moisture streaming northward here, out ahead of this low. So there's going to be a lot of moisture in here. And because it's a warm air mass riding up over a cold front here, you're going to get rain probably to the north side of that front. Precip back in here. Another thing, though, with that cold front, it's 78 here and 63-degree dew point. Well, look to the west. Yeah, 73. It's just slightly cooler, but look at the dew point. It's 33. Here it's 24. Very dry air coming in from the southwest. Remember, we saw that dry thing on the water vapor imagery coming up there. Well, sometimes it even reflects itself at the surface, so you can actually see the dry air right there. So let's move forward with time a little bit and take a look at some jet streams here. Jet streams tell you lots of information. I'm looking down from the North Pole. The North Pole is right up here, and one of the things we've been talking about is how the projections that we use in weather to look at weather maps and how they maybe one of them comes right at the side of the earth and another one looks down from the top of the earth. Well, this is looking from the top of the earth. Have a very strong jet stream out over the Pacific coming in, just bubbling up and down. If you were to look at it here, you have low pressure. It's right over, almost over the North Pole. And that's many times that happens in the wintertime. And then branches at that low. You have one branch coming down here, pretty broad over the Pacific. You have another one here. One of the things I wanted to show here, we have a very high pressure. And notice how the jet stream almost goes due north here, just a little bit off the east coast of the United States. What that's doing, and then it cuts back into here, what that's doing is as these lows and this all this band of high winds is coming in here, it can't make this turn that fast. So what it's doing is blocking up, and that's why you're getting this low here, another one back in here. They're all wanting to go through here and go right on back around and come back around to the other side, but they can't. This big high is blocking them. It's causing them to become little balls, literally little low pressure systems each along the way, and slowing them down so they can't move. So until this high finally gets out of the way and moves away, you're going to slow down the pattern of wind across the United States, and you're going to wind up with a lot more of these low pressure systems gradually bubbling up. And because of where the high is there, you're going to have a pretty steep trough right alongside of it, just off the East Coast. But then you have high pressure that's just inland of the East Coast of the United States. This is a very typical springtime pattern in many ways. You get lots of these lows coming along here, and they wind up eventually literally undercutting these highs. That'll just be sitting up here and trying to keep the flow from moving that fast. So it's kind of a fun pattern to watch. And we're going to look through it here. We'll just start it up and see how it's moving along. One of the things, this is a very classic low. You see the divergence up in here, even more divergence from that. So you're keeping your low going, and it's moving very slowly because of that big block that's been sitting there. And your other lows are coming in, trying to push it, but they're having a tough time because that block is just holding everything back. So what happens is the flow gradually turns more and more, trying to go up, and then eventually around the air there to make its way around that big block. But it's slow in doing that, and you can see it's just meandering through central eastern Canada there right now, much weaker because it can't develop that strongly. And here's another one coming into the west, starting to pop down. And this is by 94 hours out. This would be on Tuesday. And you can see again over Texas. Again, you're cutting it off looking at that. So let's take a look at the next one through here a little bit. We'll look at a little bit about forecast with this all too. So here's 12-hour forecast. You can see the one low down over Texas still there. High to the north, Arctic front, fairly cold front there. Polar kind of front. Think about it, the air mass that's coming in here isn't coming from the Arctic. It's coming out from the northwest, coming off the mountains. And then that stationary front hasn't moved much. And 36 hours out, man, that low is still coming. One of the things on the East Coast sometimes happens, we call them backdoor cold fronts. I'm not a big fan of them because they bring bad weather to the eastern side of the mountains. If you live on the western side of the mountains, it's not quite as bad. But what happens is that big high you saw sitting up here causes this high to keep building. And instead of moving eastward steadily, what it does is builds down on the east side of the mountains. Well, think about it. It's got cold air. It's got east winds coming into the mountains. It's causing high pressure. It's causing the air mass to keep getting higher and higher, more air coming into the mountains, so that high, instead of being held up here, is being pushed down, and that causes this cold front to push south. So you wind up, even though the low is out here and all the Canadian air is out this way, you're winding up bringing down a high along the eastern United States with time. And you see even that cold front gets further and further down. This one's supposedly not going to make it down to my latitude, but might make it into Frederick, Maryland. So, and that once you get north of it, look at the winds. We talk about them being north here. Well, again, you got to remember that friction and all, they're going to start coming off the water. We have a pretty cold Atlantic Ocean still out here, and it's fairly wet. So you wind up with a lot of light precipitation, lots of clouds north of these fronts. And when that happens, it winds up keeping the temperatures well below normal and not very pleasant weather for several days at a time because that block is not moving anywhere real fast. So, and we can see that high is still sitting just right up there, but slowly getting pressed to the east. It's not quite in the right favorable location, and it's still trying to drag across, Pennsylvania. And also, if you were living in New York, Pennsylvania, you'd probably be looking at a lot of low clouds for the first part of the week this week. And day 5, you finally have the other air mass coming in from the west. That block's beginning to shift to the east. You have another classic extratropical storm developing there. You have another one down here in Texas. Look at all the moisture coming up off the Gulf of Mexico into that area again. Dry air coming in from the west to help the instability. So in a little while, you're probably going to have a series of thunderstorms developing out in that area as well. So this is just the 500 millibar halfway up through the atmosphere. We've talked about it a lot. What you're seeing in the colored in are what they call vorticity. All vorticity is the desire for air to spin. If you look at a top rotating real fast, well, air wants to rotate just because we live on a turning Earth. So these are where air wants to rotate the most. And you think about it, you have a low pressure system. Air is rotating the fastest under it. The same kind of thing is happening in the upper air. You're getting strong vorticity here. Where that vorticity is advecting into is where the air is trying to rotate faster aloft, also helping it to rotate below it. And that rotation also causes the lift. But it's also a great way to look at where weather systems are going to move with time. By knowing how the 500 flow looks, sometimes you can watch weather systems move very quickly along the country. So we'll just start it out here a little bit and take a peek how they move quickly. And you can see that very strong upper level low sitting over the northeast of Canada there, just sitting because it can't get through that block to the east. And then you have your other 500 low here that was over Texas today. By tomorrow, it's moved east, and by Sunday, it's coming up. And here's a little trail of, some enhanced vorticity. Might call some lift. You can see actually the wind's shifting to the northwest there, heading towards the northwest and then towards the northeast. So there, some divergence at around 18,000 feet or so with time. There's this other low still sitting out here, still hasn't gone anywhere. And that's where you see the ridge coming, building in back in here that kept that high in place. It just won't let that come down with time. So let's move on to another one here. We'll look a little bit further in the future here. This is just the highs themselves moving with time. We've already looked through this map pretty much. I wanted to show you something else today, begin to get you thinking about weather a little bit. We can't solve weather forecast equations. They just mathematically, we don't know how to do it. Nobody in the world does. So we approximate everything. So here is where your approximation comes in. This is a numerical model. And what we've done is taking several different ways of solving the same equations and just see what they do. So what you have here is contours that are all the same pressure. They're all isobars. And this is a starting out point very close to the same position. Watch how they deviate with time and how they get further and further. You can see out west, all the spread to them and all the changes in here. That's the uncertainty that's developing with time, with forecast. So I just wanted you to get an idea of that, just to get a feel for it. We'll talk more about it in future weeks here. So, all right, here is a simulated reflectivity map again from the high resolution model. Kind of neat to watch. We've talked about the moisture coming up from the Gulf Coast. Well, you can see it kind of even in little bubbles in here, a little bit of convection it thinks is happening. But what you can really see with time, that squall line coming across to Arkansas, coming into Missouri there, the southern part, Missouri, really developing. It's really beginning to pick up the moisture off the Gulf of Mexico. Look at the other front to the north. You can see the precip. That precip's all north of the cold front. Maybe right along here with a little bit more convection, maybe right along the front itself. But most of that precip's north of the front, and here is also north of the front. And if I were to talk about a conveyor belt, we talked about the Norwegian model. Well, if you look at the other model with the conveyor belt, look at this moisture coming up in here, and you'll see how it rotates back to the west here. That's a warm, moist conveyor belt that's feeding down and over top of the cold air in here. You have a cold conveyor belt coming down out of Canada, which sweeps in underneath that and brings in the cold air below it. So some of that area could even be just a little bit of snow, but it's very neat to watch on radar because radar really kind of shows it up very nicely. So we'll move along a little bit here. This is Storm Prediction Center. We talked about all that moisture coming in. We talk about instability. There's an enhanced area down in here and a slight risk and a marginal risk. So all that right in that ball game. So let's take a look a little bit at those areas. But what I wanted to show you is the discussions that are out there right now. They're issued anytime something interesting happens. So let's see what's interesting in part of Arkansas right now. This mesoscale discussion is looking really right in this area at the wind here and the severe potential. Watch concerning it. And if we can retrieve this one right here, and we'll look at it. It should come up here in a second. Yep. What it's talking about here is you got some. Oh, this is an old one. Sorry about that. We're going to look back to the other one here. There we go. All right. One of the things we talked a little bit about how winds change direction with height. Well, here you can really see it. The low-level winds are coming more out of the south, west, and south, and in the south, and then aloft becoming more southwesterly and even almost westerly and stronger. So you're getting what they call really good wind shear. And thunderstorms love wind shear. And the more wind shear they can get, the better they like it. We're going to talk a lot about thunderstorms in the future. But this is talking about that. And it's discussing how, we're going to get a shallow, linearly forced band of thunderstorms. We saw those thunderstorms on that model already, estimating it. We have some backing flow aloft at 850 to 700. We have the moisture coming in. So it was just something to talk about here a little bit. And if we look at the sounding from this morning, this is Little Rock, Arkansas sounding, right in the area where they were talking about. And we talked about moisture. And all right, the sounding is not real moist this morning. However, that dew point that was in the 40s and 50s this morning is now in the 60s. So it's way over here. So sometimes you got to think about how a sounding might change with time. And that's what it's doing right here. So instead of lifting a parcel that, is way over here and dry and you have to find where it's going to mix, well, what you're doing is you're bringing a whole lot more moisture into that sounding. So instead of it being mixed out way over here, you're actually bringing up air that's much moisture so that you wind up going like this, further away from the old sounding and staying that moisture, causing the clouds to develop, causing the temperatures to not cool as quickly in that air parcel. Remember, you're dealing with an air parcel. You're not looking at the whole air around you. You're just dealing with a parcel of air. And that parcel of air, once it got pushed through this inversion, probably has nothing stopping it until it gets up to about 200 millibars. Up around, 40,000 feet. We talked about the wind shear. Well, look at the curve here in this winds. It goes up very nicely on the photograph. So these are all things that come out looking at the soundings, learning about the instability you learned about, learning about the changes in wind direction with height that caused by friction. And now here is this actual low. Here's your low we were talking about. And here's your front. The actual, literally an occluded front. You have warm air probably that's been pushed aloft. You have cold air along it. So you can actually see it down into here. Good southerly flow into it here. Even though you still have some southerly flow, it's cooler on that side of it. One of the things that's nice to look at is dew points. So we're going to look at it in terms of mixing ratio. The higher the mixing ratio is, the more moist it is. Here's some really 300 mixing ratio is fairly moist air right in here, coming up out of the Gulf of Mexico. Not so much over in here as well. So you've got really good contrast. Your mixing ratios lines are the dashed lines right in here. So they're really pushing up lots of moisture in here. Drier air coming in on this side as well. But right in here, good strong convergence. And if you were to look at thermodynamics, I talked about Cape convective available potential energy. The higher the CAPE, the stronger the potential for thunderstorms to grow. Well, one of the nice things about Storm Prediction Center, every hour it does an analysis, and it has on these mesoscale charts the CAPE. So you can actually see where this morning we didn't know how much was going to get in here. We actually see with the Gulf of Mexico with time, there's 1,500 joules of CAPE, 1,000 joules here. Really, you want literally over 2,000 really to get a good strong squall line going. But sometimes you can get very strong winds and good lift that can still do it with less than that, and you're probably, have 500 to 1,000 joules of CAPE right in here along this squall line, so that's enough lift right now to provide it. But it hasn't got severe yet, but it could with time. So one other thing I thought I'd look at is I talked a little bit about all the various models and how you look at, we don't solve them correctly. Well, here's a plume of temperatures, and you can actually see the spread with time, forecast temperatures, and you can see they're even getting more and more off balance the further out it gets. So something like I say, we'll look about in the future. So again, if you have any questions this week, please don't hesitate to contact me. I hope this taught you something.